So adding, and so you're going to see some things written out in a formula form. In our notes, this is the only thing you see written out in a formula form. And I don't think it's really necessary to memorize the formula. Really, all this formula says is that you add and subtract like term-wise or like component-wise. Meaning, if I'm adding, you know, if I've got these two complex numbers and I'm adding or subtracting, well, I just do the addition or subtracting on the real parts. And then I do separately the addition or subtraction on the complex parts, and that's what that is. It's kind of like just combining like terms, where like your j's are like terms, right? You think of your j's as like terms and then your real parts as like terms. So if we did an example here, 3 plus 2j plus negative 5 plus 7j, well, I've got 3 plus a negative 5, and then I've got 2j plus 7j. 3 plus negative 5 is negative 2. What's 2j plus 7j? 9j. See, you're a pro. This is how we add and subtract complex numbers if it's written in this rectangular form. Yeah, see, we got it. It's just like if you added like linear expressions like 2 plus 3x, or you're sorry, 3 plus 2x and negative 5 plus 7x. It's like the same thing, right? That j is like a like term. We can make things a little bit more interesting if we just start with an expression that makes us work a little harder to get there. So we have these, okay, so we got these radicals with negatives inside. If my goal is to simplify this, what do we do first?
Take out the j.
Take out the j's, right? If I see a negative, if I have a square root of a negative, the first thing I do is I say, all right, well, this minus here comes out as a j. So this is 3j times root 4 minus 4 minus, and then I have 6 minus, let's see, here's a negative. That's going to come out as a j. So 2j root 25 minus, and then one more here, minus j root 81. These are sort of nice convenient numbers to have inside the radicals because they're all perfect squares. Root 4 is 2. Root 25 is 5. Root 81 is 9. So our very first term here now is going to be 6j minus 4. And I'm deliberately just trying not to do too many steps in one go because I feel like at least I am more likely to make mistakes then, right? So I'm keeping everything in their parentheses. I'll worry about distributing the minus sign through these parentheses after I've dealt with this arithmetic. So this would be 6 minus 10j. And then we have minus 9j at the end. Yeah. Oh, yes. Who else was not here last class?
If you did it.
Everybody gets notes. Okay, what comes next? What should we do next? Yeah, why don't we go ahead and do that, right? I mean, at this point, we just want to get to a point where we can gather our like terms together, right? So the first set of parentheses here aren't even needed, right? There's nothing, we're not multiplying anything by them, so I'm just going to drop those parentheses. And then distribute this negative, so it becomes minus 6 plus 10j, and then we have a minus 9j. And then we just combine our like terms. So negative 4 minus 6, well, that's a negative, kidding, minus 10. And then we got 6j, 10j, and a minus 9j. What does that give us? 7j. So, and it's a positive, right? So plus 7j. Huzzah. So I think, you know, we are already sort of had the skills to do, you know, add and subtract complex numbers. And, you know, I've got good news for everybody. We pretty much already have the skills to do the multiplication and division too. The way that we approach the multiplication and division, you know, remember that j is the square root of -1. And when we're working with a complex number in this rectangular form, the a plus bj form, it's just like when we did arithmetic on the, you know, radical expressions before. So those same techniques that we use to multiply and divide radicals will work just fine to multiply and divide complex numbers. So I often start out, and in fact I did the same thing when we were just working with radicals generally, is start out by simplifying. Here I'm going to simplify the complex numbers, so I'm going to write them in like the rectangular form, meaning when I see the negative inside a radical, I'm going to pull out the j. So we have 6 minus j root 4, and then times j root 9. May as well go ahead and call root 4 2 and root 9 3. So we have 6 minus 2j in parentheses times 3j. Now what would you do to multiply these? Yeah. We have sort of algebraic instincts here that will serve us well. So 6 times 3j is 18j, and then we have 2 times 3 is 6. We have a minus 6j times j is j squared. It might be tempting to leave it here, but when we multiply two complex numbers in rectangular form, we ought to be able to get another complex number in rectangular form, meaning a real part and an imaginary part. Here we have a j part, the imaginary part, and a j squared part. So what do we do with that? J squared is equal to -1. So we use that, you know, basically our new fact for the chapter, j squared is -1. And so this is 18j minus 6 times -1, or 18j plus 6. It is fine to write it in this form. You'll see in the back of the book they default to putting the real part first. Either way is fine. You know, they're equivalent. You want to do another?
Oh yeah.
Oh yeah. What do your instincts tell you about this one?
Put the real numbers and imaginary numbers together.
Yeah, well, sort of. We're not adding them, so we're not ready to combine like terms yet, because they are already, like, each number is written in a rectangular form. I've got a real part and an imaginary part.
How about we FOIL?
How about we FOIL? Yeah, we're multiplying two binomials. So I'm going to set up the little grid here. So 2, 3j, 1, -5j. So 1 times 2 is 2, and 1 times 3j is 3j. Let's do the bottom row. What do we get to start off?
10j,
-10j. And now what about this one? What goes here? 15?
-15j squared.
Yeah, so we end up with a 15, and the reason is because -5j times a positive 3j is a -15j squared, and we know that j squared is equal to -1. So if you multiply -15 and a -1, you'll get a positive 15. I almost always write this out just to make sure. As you can imagine, sign errors can be really easy to make when we're doing this arithmetic, because we end up with a lot of j squareds or j cubes running around. So, all right, now we have our like terms on these diagonals. So 2 plus 15 is 17, and 3j and a -10j is -7j. So our product is 17 minus 7j. Okay. Now here comes the fun part. If we want to divide real numbers, or sorry, complex numbers, it's just like when we were dividing radicals. You know, this is the 10th time I've said this today, but I'm going to just repeat myself again. J is simply the square root of -1. When we're working with a complex number in rectangular form, it's just like when we worked with the radical expressions. So when we divided radical expressions, you know, if I wanted to take, I don't know, 1 over 3 plus root 2, what would we do to do that division? Yeah, what do we call that? Yeah, so we multiply by the conjugate of the bottom, 3 minus root 2. And, you know, the top in this case ends up being a boring product. It's easy to multiply anything by 1. And then the bottom we just have to FOIL. FOIL or make the grid, but we get 9 minus 4. So like 3 minus root 2 over 5. I think I did that quickly in my head. But oh no. 9 minus 2. See what happens when I do things quickly in my head? So this is when we're dividing complex numbers in a rectangular form. It's really the same scenario. So if I have a complex number in rectangular form in the bottom that I'm dividing by, we multiply by its conjugate, its complex conjugate. Note that regardless of the order that these terms might be written in, with the complex conjugate, we always change the sign of the imaginary part. And here that works out just the way we would expect. So we multiply top and bottom by 3 minus 4j. And now we have a couple of products to find. Okay, so let me do the top product first. 7 minus 2j, 3 minus 4j. We get, let's see, what do we get on the top row?
21 and then -16.
Mm-hmm. How about the bottom row?
8j squared.
Yeah, 8j squared, which is negative 8. Good. So, on top, our real parts, we have 21 and a -8. That ends up being 13, I think. And then for the imaginary parts, 28, negative 28j and negative 6j is a negative 34. Okay, so the numerator we got. The bottom, now we're going to work that product out, and let's keep in mind the whole reason that we use this technique. I'm going to scroll back up to this little example we did ahead of time. The whole reason we use that technique of multiplying by the conjugate is because I got rid of the radicals, right? So we ended up with just a nice rational number in the bottom. Now, the way that works out in this context when we're dividing complex numbers, if we're getting rid of the radicals, what that means is that we're getting rid of the j's. So if we do it correctly, the reason we multiply by the complex conjugate is because that product should just give us a real number with no j's in it. That's not imaginary at all. So let's keep that in mind. Now let's set this up and see what we get. That's just sort of that's a check, like a sanity check you do at the end of this. So we have 3 plus 4j, 3 minus 4j. What do we get in the top row?
9 and 12j.
Uh-huh. And on the bottom?
Negative 12j. And negative 16j squared, which is 16.
Yes. Good. So notice on On this diagonal here, our imaginary diagonal, these guys cancel. That's what's supposed to happen. And then we're left with 9 plus 16 is 25. Now, if you divide it, you'll notice there's no common factor up top that we could take out, so it's not like we could reduce this at all. And if you wanted to leave your answer like this just in general when dividing, I wouldn't really take issue with it, but be aware of two things. One, in the back of the book, they're not really going to write it exactly in this form, and we'll find the form that we're going to write it in just a second. But if you're being asked, write the result in rectangular form, we know that we have to actually make one more step here. Because we don't have a number that's written exactly in rectangular form here. What we have is a number in rectangular form divided by 25. So one small step to make sure it's written in rectangular form, if I want to write this as a real part plus its imaginary part, just split up this fraction. And that's how you'll see it in the back of the book, probably. It's useful because sometimes maybe they'll ask you a question like, oh, what's the imaginary part of the result when you divide, blah, 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 right? So if I just leave it in this form that we got initially, I might look at that and say, oh, it's negative 34 is the imaginary part, because that looks like it's the coefficient on j. But really, the imaginary part is negative 34 over 25. You want to do another one? Yeah. Oh man, we're adding fractions. Yeah. It's one of my favorite things. So we have a couple of ways we could proceed. We could either do the division first, right? Like deal with the fractions first, and then add the results. Or we could get a common denominator first and then do the division.
I think it makes sense to have a common denominator first.
Okay. So if we do that, then this fraction needs 3 plus j on the top and the bottom. This fraction needs times j, because the denominators have no factors in common. So our common denominator then is j times 3 plus j. And up top we have 3 plus j plus 2j. Bless you. Now what? Yeah, I think I would distribute the j on the bottom. And what about on top? Yeah. So we got 3 plus 3j. And then if we distribute that j on the bottom, we have 3j, plus j squared. J squared is, of course, negative 1. So I think I'll write this as, 3 plus 3j. If I write this, I'll put the real part first. Negative 1 plus 3j. Oh yeah. We haven't done any division yet, right? How do we divide? Say that again? Yeah, so we got to multiply the top and the bottom by the complex conjugate. And what is the complex conjugate? Mm-hmm. All right, well, let's find some products. Let's do the top. I'll do the top first. 3 plus 3j, and then negative 1 minus 3j. What do we get in the top row?
Negative 3j.
Bottom row?
Negative 9j.
Negative 9j.
And negative 9j squared, so...
Yep, positive 9. Great. So overall, On top, we have negative 3 plus 9. That's a positive 6. And then in the imaginary diagonal, negative 3j minus 9j, negative 12j. Let's do the product on the bottom. And we know, going into this, that if we do it right, this product in the bottom should be real, right? There should be no imaginary part to the what's left. Top row.
1 negative 3j.
Bottom row.
3j and negative 9j squared equaling 9.
Yeah. Great. Good. So what do we get for the real part?
10.
And the imaginary part? Nothing. They cancel out. So if we want to write this in rectangular form, we should split this up. And then, of course, probably reduce these fractions. So we get 3/5 minus 6/5 j. Yeah. Notice that we can answer questions like, so I guess I'm going to do this in this little tiny piece here. Don't worry, it won't take long. Like, what is 1 over j? Like, what's the reciprocal of j? How do we answer that question? Why negative j? Okay. So if we think about what is 1 over j, like what's the reciprocal of j, why don't we think about it in terms of what's the operation that we want to perform here? What? Division. So can we divide 1 by j? I hope so. We just did some division, right? How do we divide by a complex number?
Multiply by j.
Yeah, we'll multiply by the conjugate, and what's the conjugate of j? Negative j. So really we would say let's multiply by negative j. So we get, on top, minus j. On the bottom, j times negative j is a negative j squared. What's negative j squared?
1.
Yeah, positive 1. So this is just negative j. Negative j was right. So we have the ability to sort of ask and answer these types of questions, the things that felt very natural, like we know what 1/3 is as a value. So it turns out 1 over j is negative j. And that's interesting. Everything's interesting, but I'll tell you why this is interesting. You know how we spent some time looking at powers of j? Yeah, last time, so we know what j to the first and j squared, and we said, oh, there's this pattern of these powers of j that appear. So now we know that j to the negative 1 is equal to negative j. We can actually extend that pattern. That pattern extends into these negative powers. Okay, enough fun. Back to business.
Oh, it's all fun.
Yeah, well, speaking of powers of j, I got some going on in this problem. All the way up to j to the 5th. So j to the 1st is obviously j. What's j squared?
Negative 1.
And j cubed? Negative j. And j to the 4th? 1. J to the 5th?
J.
J. Okay. I'll stop there. So we just sort of worked out like what each of these powers of j is, so let's plug them in. So 3j squared is 3 times negative 1 minus 2 times j cubed is negative j. 5 times j to the 4th is 1. J to the 5th is j. And we're raising this all to the 6th power. Now, initially you might look at, like before we made any of our substitutions, right? If any of you were thinking, boy, I'm going to have to FOIL this whole big thing out 6 times, that you could. I mean, I'm not saying you can't do that. You could, and if you work very carefully, you will eventually, in a day or so, arrive at the correct answer. But we save ourselves a lot of labor and a lot of sort of potential for making like little mistakes that as we sometimes do when we're doing a lot of algebra, if we simply, utilize what we've already, what we know about these powers of j first. So now this is minus 3, and that's plus 5. So this is 2. And then we have, what is this part? Plus 2j. And at the end, negative 2j. Is that okay? No? Let's see. So 3 times negative 1, I'll just pull these down. So 3 times negative 1, definitely that's negative 3. Negative 2 times a negative j is a positive 2j. 5 times 1 is a positive 5, and obviously then we have that negative 2j at the end. So let's combine like terms. The 2j and the minus 2j here, they cancel. Negative 3 plus 5 is 2. So this whole thing is just 2 to the 6. Even if, so it's much better to do this substitution, but even still, oh, how psyched are we that it just ends up being 2 to the 6? Because even if we boiled it down to like something with both a real and an imaginary part, raising that to the 6th power would still be a pain in the ass. This, though, not at all, right? What is 2 to the 6th power? 64.